Hey guys, how you doing? It's Mr. Lee. This is a continuation of our lecture from earlier today or yesterday, depending on what period you're in. This is the conclusion of the lecture on 6.3. So one of the really big useful tools that you're going to learn in 6.3 is how to make and how to read a tree diagram. I find that tree diagrams are really useful tools for figuring out compound events, figuring out probabilities. So in section 6.2, we learned about the sample space S. And another way to model this chance behavior that involves a sequence of outcomes is to draw a tree diagram. So for example, let's think about flipping a fair coin twice. What is the probability of getting two heads, HH? Okay, well, if we just use H, capital H, to represent the outcome of heads, and T, capital T, to be tails, well, these are the different possible outcomes that could happen. Okay, you could have a head, then a head, a tail, TH or TT. So HH, HT, TH, or TT. So the probability of two heads is the probability of HH, which is 1/4. Okay, because each one of these is equally likely to occur. So this is how we draw that in a tree diagram. So we start off by tossing the coin one time, the first time. So this is the first toss. And on the first toss, there's only two possible outcomes. Either we can have a head or we can have a tail. So the outcomes are right here, H and T. They're at the end of this first sort of branch, okay? And the associated probabilities are written in the middle of the branches. So 0.5 or 1/2 right here, and then 0.5 or 1/2 right here. Okay. So after the first toss is concluded, you have an H or T, and then our second toss takes place. So if let's say we got a head on the first toss, we toss the coin again, we can again either get an H or a T, and these probabilities again are 1/2 and 1/2, okay? And the other thing that could have happened on the first toss is you could have gotten a tail. So this could have been the first outcome. And then we toss it again, and you can get either an H or a T, and again, those probabilities are 1/2 and 1/2. So when you look at each toss, so here's a toss right here, these probabilities add up to 1 because that's the entire sample space. And then on the second toss right here, these probabilities add up to 1 because that's the entire sample space. And then same thing here. Okay, so the probability of getting two heads, well, that is this upper branch here. You got a head the first time, and then the upper branch again, you got a head the second time. So it's the probability of HH. So what you do is you multiply these two branches, these two probabilities, 1/2 times 1/2. So the probability of two heads is 1/4. Okay, now I'm going to show you a little bit more with how to use this tree diagram. So let's do a couple more examples. So before we do a couple more examples, I'm going to teach you what is called the general multiplication rule. When you have two events, A and B, the general multiplication rule, and this is the only thing you need to memorize. There's a special multiplication rule for independent events, but it doesn't matter, okay, because it's the same as the general multiplication rule. So the general multiplication rule is this. If you have two events, A and B, okay, the probability of A and B occurring, because remember this upside down, this symbol means intersect. So the probability of A intersect B, and in common English that we use for intersect, we use the word and the mathematical operation is multiplying, right? So the probability of A intersect B is equal to the probability of A times the probability of B given that A has already occurred, okay? So this is a very important rule to memorize. This is worth writing in your notes, okay? So the probability of A intersect B, or in other words, the probability of A and B both occurring is equal to the probability of A occurring times the conditional probability of B given that A has already occurred. Now, This is true even if A and B are independent. Okay, but how does this equation change slightly if A and B are both independent events? Okay, well then you know that the probability of A and B occurring is just the probability of A times the probability of B. Okay, how come this becomes just probability of B if A and B are independent events? Because we know that the probability of B is equal to the probability of B given that A has already occurred if they're independent events. Okay, so this general multiplication rule is true for two events A and B that can happen together, or excuse me, that are independent or are not independent. Okay. Okay, so this is a really important example. I'd like you to draw this one in your notes, okay? So this example has the Pew Internet and American Life Project. And remember, this is a very old study, okay? But it found that 93% of teenagers from ages 12 to 17 use the internet. Okay, and again, this is very old information. This is, I don't know what the date of this study is, but I know that this textbook was published in 2010. So this is probably older than 2010. But anyways, here we go. So we find that 93% of teenagers from ages 12 to 17 use the internet, and that 55% of online teens have posted a profile on a social networking site. So the question of interest is, well, what percent of teens are online and have posted a profile? Okay, so here is the tree diagram. So out of all teenagers, we're going to randomly select one teenager. Okay, and then out of all these teenagers, okay, we're going to see, are they online? Is this particular teenager online or not online? Okay, so if they're online, then we're going to go to this upper branch, which is yes. The answer is yes, they're online. If they're not online, then the answer is no, they're not online. And we were given that the probability of online is 0.93. So we write that given probability right here. The probability that they're online is 0.93. Well, then the answer no, this is the complement of being online, right? So the probability of no is just 1 minus the probability that they are online. So it's 0.07. Okay, and again, since we only have two branches for this first decision, okay, or this first branch of our tree, okay, these have to add up to 1, okay, and which they do. So now, if we follow this yes, so now we're only looking at the students that are online, okay, that are yes online. And then we ask the student, well, do you have a profile? Have you posted a profile of yourself on a social networking site? Well, there's only two possible options. It's either yes or no, okay? And we're given that this probability is 0.55, and so this is the complement, so that's 0.45. So it's either yes, they have posted a profile, or no, they have not posted a profile. So it's 0.55 and 0.45. And so down here, okay, now where did we get these probabilities? Well, think about these probabilities, okay? We asked this teenager the same thing, okay, and this teenager has already answered no. Okay, I'm not online. Well, if you're not online, could you possibly have posted a profile online? Well, absolutely not. So the probability is 0. There's 0 probability that this particular student posted a profile online if they're never on the internet. Okay, if they do not use the internet. And then the probability that they have not posted, okay, given that they're not online, it's a certainty. So the probability is equal to 1. Okay, and again, these two probabilities, these all add up to 1. And there could have been, if you had more than just two decisions, more than just yes or no, if there's many different branches coming out here, they would all add up to 1. Okay. So now, this is how we read this tree, okay? So we know that the probability of a randomly selected teenager being online is 0.93. Okay. We also know that the probability that they have posted a profile given that they are online is equal to 0.55. How do we know that this is a conditional probability? Because of the wording here. 55% of online teens, so that is just out of the online teens. So that is the condition that is being met. So just out of online teens, 55% of them are yes, they did post a profile. So that 0.55 right here is this conditional probability. This is not an intersection. This is not an and. This is a given that. Okay, so let's just think about that for a moment. So we start off with a randomly selected teenager, and then the first question we ask them is, are you online? And if they say yes, okay, then out of the online, or given that the student has already responded yes, or given that we know yes, they're online, what is the probability they have a profile? So this is yes profile, given that we already know that they're online. That is why it's a conditional probability. Okay. But the question is, what percent of teens are online and have posted a profile? Is that 0.55? No, the word and is intersection, right? So this question is asking us, what is the probability of online intersect profile? Not given that. Well, how do we get that? Well, where is that on this tree diagram? Well, that is right here at the end of this last decision, or at the end of this last node, okay? Right here would be the probability of yes online and or intersect yes profile, okay? And how you calculate this probability is you simply multiply these two probabilities from these two branches, okay? And if you look at our general rule for multiplication, here it is right here. To calculate the probability of an intersection of two events, it's the probability of A times the probability of B given A. Okay, so if you think of A as online and B as profile, then the probability that they're online and have a profile is the probability of online times the probability of profile given that we know that they're online. Okay, so that probability is going to be right here, and I'll show you by filling in the rest of this tree diagram. Okay, so here is just our general multiplication rule for two probabilities, or for an intersection. And how do we actually calculate it? We multiply the two branches, so it's 0.93 times 0.55. So this probability, this intersection, the probability of online and profile is 0.5115. Okay, so that tells us that approximately 51.15% of teens are online and have posted a profile. Okay, remember, this is an estimate of what we believe the true proportion of teens that are online and have posted a profile is. Okay. Now I want to break down, or actually, I want to break down and fill in this tree diagram a little bit more thoroughly. So this is the most important thing about tree diagrams, is this next slide. Okay, so I've enlarged it so it's easier for us to see. And this wasn't supposed to be there yet. That's supposed to be animated, but I missed an animation. Sorry. Okay, so here we have, this is just the exact same tree diagram. I just enlarged it. And let's define O, capital O, as the event that the teenager is online. And I couldn't use P, capital P, because capital P stands for probability. So I used R. So let's use capital R as the event that they have a profile. Okay. And we are given that the probability of O is 0.93. That's kind of our starting point. Okay. So that probability is right here, okay? So this 0.93, that is the probability of O. And then obviously this 0.07 is the probability of the complement of O, meaning this is the probability that they're online. This is the probability of not online. Okay, that is equal to 0.07. Probability of O is equal to 0.93. Okay. Now this probability, this is critically important that you know that this is the conditional probability, because we've already established that yes, they're online. So the condition is given that yes, they're online, or in our case, because we're using O and R. So given that O has already occurred, what is the probability of R? Okay, so again, you read this statement, what's the probability of R given that O has already occurred? Okay, and that is this right here, 0.55. So what would be the notation for 0.45? What is that? Well, this again is a conditional probability. This is the probability of not R, meaning they have not made a profile, but given that, yes, they're online. So the notation for that is this: the probability of R complement given that O has occurred, and that's equal to 0.45. So can you figure out, okay, what the notation is for these two probabilities, this 0 and this 1? Okay, pause the video and figure out what those are. Okay, so this probability is the probability that they have a profile given that they're not online. Well, that's going to be a 0. That's certainly going to be 0, because if they're not online, they can't have a profile. They can't have made a profile. Okay, and then what is the notation for this? Well, that is the probability that they do not have a profile given that they're not online. Well, that's a certainty. If they're not online, we know for sure they have not made a profile. Okay, so that is a probability equal to 1. Okay, now here's a critically important part. So what was that thing at the end here that I showed you? Okay, where you multiply the two branches, that is your intersection. So these 4 nodes at the very end of your tree diagram, that's where your intersections are. So inside the tree diagram, after the first decision is made, these are all going to be conditional probabilities. And you could have another conditional probability, another set of branches. That would be another conditional probability, but we're not going to make you do that, okay? Because we're not going to do like triple compound conditional probabilities. Okay, we're just going to go with 2 decisions. And then this is going to be your intersection. So all your intersections come at the very end. Okay, so this is the intersection. So this is the probability of O intersect R. And that is equal to, you just multiply the 2 branches. So go ahead and figure out, well, what's the notation for these last 4 nodes? You guessed it. This is the probability of O intersect R complement. So this is a probability that someone is online and not made a profile. Okay, this is the probability of O complement and R. Okay, so this is probability that they're not online and they did make a profile online. Well, that makes no sense. That's a 0. And then this is a probability that they're not online and they don't have a online profile. So now if you add up all of these intersection probabilities at the very end of the tree, they will all add up to 1, because these are all 4 of the final cases, okay, of what could actually happen. Okay, so here's another a slightly more complex. Okay, this is a slightly more complex tree diagram. And in this case, the only thing that's more complex is that starting from the very beginning, it's not just binary. Okay, there's 3 different decisions here. Okay, there are 3 different outcomes, I should say. So 18 to 29 years old, 30 to 49 years old, and then 50 and over. Okay, so out of all adult internet users, approximately 0.27 of them are between this age, 0.45 are between this age, and 0.28 are approximately this age. Okay, and then we want to know what percent of all adult internet users visit video sharing sites. Video sharing sites. So now here, of the 18 to 29-year-olds, we know that 0.7 are yes. Okay, so 0.3 are no. So again, these are the conditional probabilities. So this is the probability of video given that it's an 18 to 29-year-old. Okay, and then same thing, here's conditional probabilities, here's conditional probabilities, and then here are all the end probabilities, which are the intersections. Okay, and then how do you get this? You just multiply 0.27 by times 0.7. You multiply the two branches to get this end probability. All of these end probabilities are going to add up to 1. And then look at the question. The question is what percent of all adult internet users, so out of all of these, what percent of them visit video sharing sites? Well, there's 3 yeses. There's video yes, and video yes. So you have to add those 3 up. Okay, and that is what you get, where you're getting the 0.4913. Okay. Okay, so for independence, like I said, there's a special multiplication rule. Okay, because if events A and B are independent, then we know that the probability of B, given that A has already occurred, well, it's still just the probability of B, meaning A occurring has no impact. It doesn't change the probability of B. So now you can just do probability of A intersect B is just probability of A times probability of B. Okay, you don't have to use this here because these two things are equal. Okay. So here's another example. This is our last example. So following the Space Shuttle Challenger disaster, it was determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under cold conditions, it was estimated that the probability that an individual O-ring joint would function properly was 0.977. Well, not good enough, right? Not a tight enough tolerance, because obviously there was a disaster. Assuming O-ring joints succeed or fail independently. Okay, that's very important. Okay, so we're assuming independence. What is the probability that all 6 will function properly? Okay, and we want a high number here because obviously we want the Space Shuttle Challenger to not, explode. So what's the probability that all 6 would function properly? Okay, so that is this. What is the probability that joint 1 is yes, okay, and joint 2 is okay, and joint 3 is okay, and joint 4 is okay, and joint 5 is okay, and joint 6 is okay? Well, if these are all independent events, you can see what we're going to end up doing. We're simply just going to multiply each one of these, okay? And so that's just 0.977 times 0.977 times 0.977 times, so it's just 0.977 to the 6th, which is 0.87. Okay, so there is 87% chance that all 6 rings will be okay. Unfortunately, obviously, we were in the 13%. So here's your general multiplication rule that you need to know. Okay, the probability of A intersect B is equal to the probability of A times the conditional probability of B, given that A has occurred. Now, we can just simply rewrite this. Okay, let's just divide both sides of this equation by probability of A. So throw that underneath there. And now you get the formula for conditional probability. So the formula for conditional probability of B given that A has occurred is equal to the probability of A intersect B divided by the probability of A. And that comes straight from our general multiplication rule. Okay, so this is actually a very nice formula to memorize, but you can just memorize either one of those, and then obviously this is just rearranging this. Okay, so now if we look at this, if we look at a Venn diagram, okay, in section 6.2, we noted that residents of a large apartment complex can be classified based on the events A. So event A is reads USA Today. Okay, so A complement is they don't read USA Today. USA Today is the name of a major newspaper that used to be around a long time ago. Okay. And then event B is they read the local, the New York Times. So they read the national news and they read the local news. Okay. The Venn diagram below describes a residence. Okay. So this yellow circle here is event A. This blue circle here is event B, and then the green intersection is both A. So it's A intersect B, okay? So what do we have? So we know that A intersect B is this 5% or this 0.05. The probability of A, okay, all of A is the entire yellow circle. So it's 0.35 and 0.05. So you have to add both of those up. So the probability of A is 0.4. Okay, and so what do we know? So what is the probability if we randomly select somebody out of this entire sample space? What's the probability that they read the New York Times, given that we know that they already read the USA Today newspaper? Well, to calculate this probability, okay, this doesn't show up on here, so we have to calculate this by using the general multiplication rule, right? So that is the probability of A intersect B divided by the probability of A. So that is 0.05 divided by 0.4. Okay, and that is equal to 0.125. So the probability that somebody in this sample space reads the New York Times, given that we know that they read the USA Today, is about 0.125. Okay, guys, that's all we have. I hope you enjoyed the video, and I will see you in class.